So now we want to talk about, keep talking about premixed flame, but talk about the flame structure. And we look at flame structure in different ways. We'll first talk about basically the thermal flame theory. Thermal, because it's based on a one-step global chemistry, no radicals, so all the effects are just based on thermal effects, heat release. And then we'll talk about a little bit about chemistry. Here, introduce the four-step mechanism for methane, and maybe three-step, and then we talk about the asymptotic structure of the flame. And then a little more here about maybe models to predict the burning velocity or data-driven models, and then here also flammability limits. So the thermal flame theory, as I said, is not based on radicals, which is wrong. I mean, you know, radicals are very important. This is just based on the effect of heat release, and then the effect the heat release has on the reactions. We said earlier, heat release makes the temperature go up, which makes the reactions exponentially faster. And so that's, you know, a kind of one way to, or one important effect, but again, it doesn't consider the radicals. That means also that chemistry, or the reaction rates, they become slower when you go to lower temperature. So if I sit in the burnt, or in the flame, in a premixed flame, you know there's a certain reaction rate. And now I go a little bit towards the unburnt, towards the preheat region. Temperature is lower, the reactions are more slower, exponentially slower. And I go all the way into the unburnt. Then the reactions become slower, but they're never zero, okay? Reactions are always, they're just exponentially slower, but they are still non-zero, okay? And if, let's say, the flow comes from infinity or from very far away, then, you know, now I come from very far away. The flame is very, very far away from me. So I walk towards the flame, but the reactions, they are there. You know, they're not zero, and they, you know, make the temperature slowly go up, and, you know, something happens way before the flame. So that is called the cold boundary difficulty. That's when, you know, old days when people did asymptotics with one-step chemistry, that's always a problem, because you need to assume things come from minus infinity, but then, of course, you know, reactions go off. But anyways, it's really, really interesting analysis. This here comes from here Zeldovich and Frank Kamenetsky, 1938, long time ago, and you see this says here, this was really what put combustion science on a mathematical basis. This is, and if you look at, I mean, Professor Law was talking about beauty in science. I mean, given this is a long time ago, they didn't have computers where they can just, you know, compute the flame structure and see how it really looks like. And then from this do analysis, they, you know, had to come up with all this stuff, all just with a paper and pencil. And maybe, you know, looking at flames. But, so that, I mean, that's beauty here in science. This is a really nice theory, even though it's just one-step chemistry. So here's the starting point. We have a stationary flat flame front. There's a velocity here from the left, and then just such that, you know, the flame here is stationary, sits in one point. And then, so the velocity from the left here is the same as the burning velocity. And then this is what they assumed. They said we have three different zones. We have I mean, here the temperature is unburnt, it's a boundary condition. Then here, at some point downstream, I reach the adiabatic flame temperature, and then, you know, complete conversion. And then in between is the flame. And they said we have three different regions. One is the preheat region. One is the reaction zone, you know, where the chemistry happens. And then I have an equilibrium zone downstream, you know, where the chemistry is basically done. All reaction rates are zero because, you know, equilibrium is reached. And so then this is what happens, is pretty much what we said earlier. The preheat region is chemically inert. There's heat conduction from downstream that heats it up. That's why it's called preheat region. it heats it up until a certain temperature is reached, and they say at that temperature reactions start, and so they call it the ignition temperature, and that's just a temperature that, again, I mean, there's no real transition or there's no marked ignition temperature if all I have is the exponential of minus E divided by RT. That's a gradual, even though exponential increase. But anyways, and we'll see later on what TI is really when we talk about multi-step kinetics. And so then you have the products diffuse also in the preheat region, and fuel and air diffuse into the reaction zone. And right, the reaction zone starts at TI. And then we assume one-step global chemistry. We have a reaction rate, which is frequency factor times concentration of fuel, concentration of oxygen, and then here this exponential function. And then again, after the flame front, reaction rate goes to 0 because equilibrium is reached. We have, at that point, for lean mixtures, the fuel is all gone. For rich mixtures, oxygen all gone. Stoichiometric, both reactants are all gone. So in the preheat, in the post-flame equilibrium region, either our fuel is 0 or oxygen is 0, or both. And then, so now I have three unknowns: temperature, mass fraction of fuel, mass fraction of oxygen. But as always, when we make some assumptions here, we can derive these coupling functions, coupling function between fuel and temperature, between oxygen and temperature, which means I have three unknowns, but I can replace oxygen with temperature, fuel with temperature, and then temperature is the only unknown. I have only one equation to solve. And then in the low Mach number limit here, we have the pressure is constant. Low Mach number limit, I think we said this earlier also. I didn't explain what it is. What's the low Mach number limit? That's the limit where the velocity is much smaller than the speed of sound, okay? And if the velocity is much smaller than the speed of sound, so if the velocities are large, then we need to solve compressible equations because you have pressure waves that go back and forth. And the problem is always if you have a flow where the velocity, the local velocity, is much, much smaller than the speed of sound, then, and you do a numerical simulation, then you need to have the time steps small enough that you resolve the pressure waves, right? Acoustic waves. But the acoustic waves now, they're super fast compared to the flow velocity. So I do, my time steps need to resolve the very, very fast time scales, which means the flow, the convection, doesn't happen at all. I mean, I need maybe 100 time steps to resolve a pressure wave, going from left to right. But in that 100 time steps, my velocity hasn't moved because the velocity is so much smaller than the speed of sound. So then sometimes we make this decomposition of pressure, which then leads to this low Mach. We assume this low Mach number, and the pressure is decomposed into three different contributions. One is pressure waves, and that goes with Mach squared. If the Mach number is small, we just neglect this. That's the acoustic pressure. And then the second is the hydrodynamic pressure. The hydrodynamic pressure is, what makes the flow move. And that hydrodynamic pressure, it still appears in the equations. And then the third is just the background pressure, which we call then the thermodynamic pressure. That's the pressure, and that's constant in space. It might vary in time, but it's constant in space. And that's the pressure we use in the equation of state, okay? So that's what we call the low Mach number limit. So when this has P equal constant, it means the background pressure is constant now. It's just 1 bar or whatever it is. Okay, and then, here, ideal gas law, coupling function, we can determine all of this just as function of pressure. This is what we had earlier, continuity equation just gives us that this is constant. And then, this is the temperature equation, neglecting here a few terms or making, also written in 1D. And so here we have the convection term, diffusion term, and the chemistry term. And now they make two assumptions, and these are really, really interesting because I don't know how they come up with this without knowing. I know, so I know it's right, but they didn't have computers to do these calculations. So they say in the preheat region, it's chemically inert. And then this term here is 0. So in the preheat region, I have only these two terms, no chemical source term, okay? And then, yeah, maybe that's something you can come up with. But then they also say, in the reaction zone, the gradients are so large that this term here dominates, and this term here is relative to this really small. So in the reaction zone, the convection term is basically 0, and the reaction source term is not. And when I first came across this, immediately I got my favorite 1D flame code, and I computed this. I evaluated the individual terms, and it's a really good assumption. But anyways, they didn't have the computers to check this. And then, okay, so here validity of second assumption. It really comes from the fact that the gradients become so large, because chemistry is relatively fast, gradients become so large that diffusion is just much faster than this. Okay, and then I can solve the equation in these two different regions, in the preheat region and in the reaction zone. So I start out with the preheat region. I say this term here is 0, no chemistry in the preheat region, so I have only these two. Rho U, rho SL is constant, and so you see I can immediately integrate this. I integrate this from -infinity to, some point in the preheat region, and then you see here the right-hand side, or the left-hand side here is just T minus T infinity, or T minus T unburned, or here T minus T unburned, and the other side here is lambda over Cp times the gradient at that point, minus the gradient at -infinity, which is 0, right? So this is the solution in the preheat region, and that's interesting because this here, we don't do this now, but you can also integrate this. And it gives you what kind of solution? What's the solution to this? This is something you should immediately see. When you see something like this, a red light should go on in your head. Sorry? No, not linear. Exponential. If the rate of change of a quantity is proportional to the quantity itself, it means it gets a little larger, which makes the rate of change larger. Okay? So it grows faster, it makes the rate of change even faster. Okay? So if the rate of change is proportional to the quantity itself, that gives you an exponential growth. I mean, and you see it easily, I mean, by, you see it easily, so if I have let's say dt dx is equal to some coefficient times t, then I can separate variables. dt divided by t is equal to a times dx, right? I can integrate this and I get ln t by tu is then equal to a times x minus, let's say, xu, and then take the exponential of this, and I have t divided by tu is equal to exponential of a times x minus xu, sorry. But, I mean, you just see that this separation of variables gives you the log, and then it gives you an exponential function. Anyways, and that, if you look at the temperature and the unburned, I mean, that's how it looks like, right? I mean, it looks like an exponential increase. Now you know it's an exponential increase. Anytime you see an equation like this, you should say, oh, exponential increase. Okay, good. So we evaluate this at this ignition temperature, and then the gradient at the ignition temperature is equal to, this. Okay, solution in the preheat region. Now we look at the solution in the reaction zone. In the reaction zone, the convection term is 0. And then I have just this, okay? Diffusion term and the chemical source term balance. And now, here's another little trick they do. which is really nice, because the temperature always increases in the reaction zone. Temperature is a unique function of X, okay? And X is a unique function of temperature. And so I can replace X by the temperature. So d by dx then is dt by dx, d by dt, okay? That's only because it's a unique and invertible function of temperature. And then you see I have dt by dx. Here I have dt by dx, so I can bring this inside. And I get d by dt, or 1/2 d by dt, and then dt by dx squared, right? And then I can integrate it again. I can integrate this in temperature. And now I integrate from Ti, ignition temperature, all the way to the burnt gas. And so, okay, so on the right-hand side here is a little more complicated. So I just write this as an integral, but you know, I can integrate it, and I don't know what to do with this integral here yet, because omega is kind of a nonlinear. I mean, it's a function of temperature, but it's not easily integrated analytically. So I have the gradient at the ignition temperature from the preheat region, and I have the gradient at the ignition temperature from the solution in the reaction zone. These must be the same or not? Are they the same? My coffee is gone. There's no sense in asking complex questions. So are they the same? I mean, they should be the same. I mean, it's the same gradient at the same point. It's just the one is determined from the left side, the other one is determined from the right side. Are they the same or not? Sorry? Well, I mean, they have to be the same. So you have to make them the same. That comes back to what we said earlier. This is an eigenvalue problem. There's a parameter in the problem, and you have to make it just, pick the value so that the condition is satisfied, okay? So that in asymptotics, that's called the matching process, okay? So now you have to match the different solutions. So you just say this needs to be the same as, you know, let's look at it real quick. Here this, and you see SL now needs to be determined such that the condition is satisfied, okay? So, so that's what you do, and then you get an expression for SL. For this, you need to integrate this, and you know, there's first of all, this is here, you do an expansion or Taylor expansion here to linearize the exponential term, and then a lot of assumptions here, you know, made from saying I have large activation energy, but we won't go here. You know, you can look at this, but without going into details here, this is what you get at the end. Okay, so you see we have an analytic solution now for SL, and that's you know, first of all, as I said earlier, now we can look at different parameters. You can see how the parameters affect the burning velocity here, for example. If you have a fuel that has very high burnt temperature, you see that actually makes the burning velocity very large. Okay, so for example, acetylene, we saw has very high. You remember we looked at acetylene had very high burning velocity. Acetylene, when we determined adiabatic flame temperature, there was a little table that showed acetylene and ethylene, and we saw ethane has a certain adiabatic flame temperature. Ethylene has a larger one, acetylene even larger. And you might know acetylene burns really, really fast, okay? So that is why, I mean, because it has such a high temperature. Here's T to the 4th, I mean the square root, so this is a T squared, and here this is exponentially, makes it exponentially large also. By the way, I should say this S factor here, it's just to distinguish between lean, rich, and stoichiometric. This last term becomes dominant for stoichiometric conditions where both of these are 0. this becomes important for rich condition. This becomes for lean condition. This for rich condition, and so, but it's not so important. But right. But the other thing we can look at now also is, does this tell us something about length scales and time scales and so on? So we want to look at flame thickness, flame time scales, and things like this. So this is the analytic solution that we got, from the asymptotic analysis, and we want to use this now to look at these characteristic scales. And so we start out here by, what is the, what are the processes that govern the flame speed? You have transport, so diffusion coefficient somehow must be important. And you have chemistry, so a chemical timescale must be important. Other parameters, I don't know other parameters. This is it, okay? And so you could say, okay, I have a diffusivity for the thermal energy and another one for the species. We assume Lewis numbers are 1, so I have one diffusivity and a chemical timescale. And then if from these two, I want to form a flame speed, something that has units meter per second, dimensional analysis tells me it can only be one form, okay? It can only be diffusivity divided by chemical timescale and take the square root of this, right? So if I say, what is a flame time? What's the flame time? Flame time is the time it takes for a parcel of fluid to move through the flame thickness, right? And so that would be something like this. Flame time is LF divided by SL, okay? And LF, also from these two parameters, just gives me this. And this kind of means, the flame time has to be the same as the chemical time scale. Why is that? The flame time, maybe it's more diffusive time, but in a stationary flame, the time it takes for, diffusion has to be the same as the time it takes to react, right? Because these processes are coupled. Whatever diffuses into the flame has to be burned in the same time, roughly. And so these are the same. How can they be the same? One is chemistry, the other is transport. How can they be the same? They're coupled and they influence each other. So until the point where they are the same. Now, we can also just say, okay, SL is equal to D times DC, but we have an analytic expression for SL, okay? And so I can evaluate TC from the analytic expression. I can evaluate what is the chemical timescale from the analytic expression. That's an interesting thing to do also, so that's what we do here. You have the SL is the square root, square root is the same, and then of D, but D is lambda over rho Cp, and I have lambda over rho Cp here. Lambda Cp, and then this rho, put it to the other side, and then I have a rho square actually here, lambda over rho Cp. And all the rest then has to be the chemical timescale, right? So the chemical timescale then, according to this and this equation, is this. And I can rewrite this by introducing here this Zeldovich number. I have a density ratio, and then the Zeldovich number, and then I have this here, which is basically just the reaction rate divided by the concentration of the fuel, okay? And this is interesting because if you have a reaction, so I have a reaction A plus B goes to C plus D. And now I would ask you, and this has some certain K rate coefficient. I would ask you, what's the time scale for this reaction? We talked a lot about time scale of reaction. I could think of what's the time scale for the rate of change of A. That would then be equal to minus the reaction rate here. And the reaction rate is K times the concentration of A times the concentration of B, right? And so, you know, if I now want to non-dimensionalize this is how I get my time scale. I would say, okay, so here I have introduce a reference time, right? So the reference time then also so is here. So this needs to be the reference time here to make it, you know, I mean, just divide by reference time. And then here also I divide by CA, you know, reference, and then here also multiply by CA reference. And bring this to the other side, then I have a dCA star, maybe it should be the non-dimensional, by dt star, and then this is equal to minus K times CA divided by, oh no, CA star, let's say, CA star times CB. Okay, and times the reference time here. So this here times the reference time would give me a K star. And then I can take this here to the other side and say, okay, so this is the relative, you know, I mean, dCA by dt divided by CA, that's the relative change of A is then here equal to this. So so this here kind of gives me the time scale. And so that's shown here. This here gives you the reaction rate divided by here the fuel concentration. That usually would give you the time scale of this global reaction. But you see here the time scale is actually this times the Zeldovich number. Okay, so it's different. I mean, in what I had here, there was no Zeldovich number whatsoever. Okay, and what's the Zeldovich number here? You know, it's defined like this, and it's on the order of 10. And so Zeldovich squared, that's a factor of 100. Okay, so this time scale is 100 times different from what I did here when I did not consider a flame at all. And so that is the the effect that the flame has. The flame actually, the transport changes also the chemical timescale. How does it do this? You have diffusion of reactants into the flame, and when the fusion becomes really slow, then the concentrations in the flame become lower and lower, and when the concentrations become very low, then also the reaction rate gets very low. Okay, so the transport affects actually influences the chemical timescale. That's a really important. It's a subtle but a very important aspect. Okay, which means also in flames you cannot separate transport and chemistry. The chemistry is directly affected by the transport. Okay, so that's an important aspect here. DC is not only determined by chemistry, it's also determined by the flame structure. Okay, so then, so this says the same thing here. We said earlier, Tc is equal to the flame time. That just reiterates this. And then we can also define the flame thickness. How do we define flame thickness? We could say flame thickness, just dimension analysis, is D divided by SL. Okay? Or D is equal to lambda over rho Cp, so it's this. But I could also say, graphically, I could say, how do I define the flame thickness here? I just take the maximum slope and I extend it linearly here to burned and unburned condition, and then I say this is the flame speed. So that's one graphical definition. But that I can also, and that's the interesting part. I can also remember this here was the analytic solution of the unburned. This was of the preheat region. Okay, and so here I can say the gradient, I mean, just like here for my graphical thing, the gradient I just approximate by a linear slope that goes from unburned to burned. So the TDX is here just approximated by TB minus the unburned divided by a flame thickness. You know, this is approximating the slope by this line. And then if I plug this in, I can solve this for LF, and then LF is just lambda over rho Cp times SL. It's the same as above here. So that flame thickness that we got just from very simple scaling, dimension analysis, is actually the same as a graphical construction of the flame thickness, okay? So that gives you a definition of the flame thickness. Okay, so all of this up to this point was a one-step global reaction, but we are interested in, you know, what's the effect of multi-step chemistry, and specifically what's the effect of radicals. And for that, we need to introduce chemistry, but we want to introduce a simplified version of the chemistry so that the analysis is not too difficult. So for that, we use then what's called the four-step mechanism. So this reiterates here just what I said earlier, that in one-step chemistry, everything depends on the temperature, and you know, you do get a large sensitivity here to the temperature, but in reality, we need to use multi-step chemistry. Now, talking just, you know, a little bit, I mean, many of you take the chemistry course in the morning, you get a lot of details on the chemistry. Here, I just want to highlight a few very simple things for those who are not so familiar with chemistry. So now here we're talking about, as an example, methane as a fuel, methane chemistry. And there are many reactions, but there are some reactions which are really important. You know, the whole thing doesn't work without a few of these reactions. The first one is an initiation reaction. Sometimes, actually we don't need this for flames, but if you had auto ignition, you just, in the beginning, you just have fuel and oxygen, you need something to create the first radical. That would be initiation. Here, thermal decomposition gives you radicals, or here for hydrogen, you know, hydrogen plus oxygen or so. Here we don't actually need these, because in flames, you know, you have radicals downstream and they diffuse upstream, and so you always have radicals. Then you have the chain propagation reactions. This is consumption here of the fuel with a hydrogen radical forming methyl plus H2. This is usually how the methane in a methane premixed flame is consumed. Then we have chain branching, radical producing reactions, and chain breaking reactions. This is actually wrong in your handout. In your handout, I mean, this lists the reaction H2 plus O. Goes to OH plus H. I don't know how this made its way there. For me, this is not a chain branching reaction, as you will see later on. But this here is the reaction I mentioned to you already. This is the most important reaction in combustion because it is for basically any given fuel. I mean, that involves hydrogen, let's say. This and an oxidizer that involves oxygen. This is the main chain branching reaction. This is what creates radicals, which leads to exponential growth and all of this. And then we have chain breaking reactions. They're different ones. This here is obvious chain breaking. H plus H goes to H2, but these are not the most important ones. I'll show you the most important one later on. Now, for those of you who are not so familiar with chemistry, combustion chemistry is very simple. If you follow five rules, okay? So rule number one. The reaction progress is determined mostly by radicals, okay? So the radicals really control what goes on. That's an important rule. Second rule, radical balance is therefore the most important aspect. So the first thing you do when you see a reaction, and nobody asked the question yet. If you just see a reaction, you count the radicals left and right, okay? And you think, oh, does this produce radicals, consume radical, or is it radical neutral? okay? Most radicals are actually radical neutral. They're just chain propagating. They make stuff from large to small, they oxidize a little bit, and so on. These are also not the most important reactions. They are important because, you know, without these reactions, there's no progress, but they don't determine the dynamics. These are reactions that are, you know, they don't determine the dynamics. And then here, of course, chain branching, chain breaking, these are the most important because they will change the radical balance. And you know, I said this earlier, if you have a reaction that makes radicals, you have more radicals which will usually make that reaction faster. You know, and so again, that leads to exponential growth. And similarly, you know, if you have a reaction that consumes radicals, it will make that reaction slower, and that leads to an exponential decay. So chain branching, chain breaking, really important. The most important radicals are H, OH, and O, and maybe sometimes also H or 2, but here really we talk about H, OH, and O. And what's interesting also, these are pretty much, they count the same in terms of being able to participate in reactions. So if you have a reaction that consumes, for example, here this one here consumes an H, but it makes an OH and an O, okay? So it doesn't make H radicals, so how does it make itself faster? Turns out, there's always a balance between these radicals, O, OH, and O. You have reactions which we call the fast shuffle reactions. They convert O into OH, OH into H, H into O, you know, all back and forth. Which means if you create an H radical, if you create an OH radical, it's just like creating an H radical, you know? Because if you create a lot of OH, a big part of this will actually be converted into H. So we don't, in the number, we don't distinguish between each individual one. We just say we increase the radical pool, okay? So these are the 5. So if you know these, everything's good. No, not yet. There's rule number 6. And rule number 6 is the O radical counts twice. Okay? That's important when you do the radical balance. Always remember the O radical counts twice. Why? Because you have 2 free valences on the O radical, and on the O and OH, on the H and OH, you have only 1. Okay? So an H radical, it combines with another H radical and then it's gone. So it has only 1 free valence. And OH also combines with another H radical and then it's gone. The O radical, you combine it with an H, you still have an OH now, okay? It's still a radical. So that's why it comes twice. And you also see this in these fast shuffle reactions. You see here H2 plus O goes to OH plus H. Is this radical consuming or radical producing? And you see, what is it? Does it consume or produce radicals? Who thinks it produces radicals? Who thinks it consumes radicals? Who thinks it's radical neutral? Okay, why is it neutral? O radical counts twice, okay? I have 2 radicals on the left side, 2 radicals on the right side. It's radical neutral, okay? This one here, 1 on the left, 1 on the right. This one here, 2 on the left, 2 on the right, okay? These are all radical neutral. They are in partial equilibrium. They go back and forth very quickly. And all they do is, you know, shuffle OH into H into H into O, you know, back and forth. Okay, so if you know all of this, combustion chemistry is very simple. You know, this is a reaction mechanism with some reactions. You see here, in our notation, the most important reaction is always reaction number 1, okay? Reaction number 1 is O2 plus H. And by the way, I just want to say this. Here, in your handout, for chain branching reaction, this one is listed. And you find this in many textbooks, combustion textbooks. In my notation, this is not a chain branching reaction. It is not, because it will not give you new radicals. It will just, you know, convert this, which counts as 2 radicals anyways, into two other radicals, okay? So my notation here is different from maybe what some other people say. But I think this is easier to understand. So number one is this. Number 2, 3, 4 are these fast shuffle reactions. Here, unfortunately, is always the reverse reaction is also listed. Fast shuffle reaction. And then here we have, yeah, this is important. And then this one here is also important. This is actually the most important chain breaking reaction. This is the reaction that consumes radicals. H plus O2 plus M goes to HO2 plus M. Why does this consume radicals if I have one radical on the left and have one radical on the right? That is because the HO2 is a radical, but it likes to be consumed with, let's say, these two reactions here, 6 and 7. H plus HO2 goes to OH plus OH. Okay, that's propagating. But this one here also happens. HO2 plus H goes to H2 plus O2. And then also this happens here. HO2 plus OH goes to H2O plus O2. Both of these are chain breaking reaction, okay? So if you have 3 reactions that go on, 2 of them are chain breaking, 1 is propagating, the net effect, radicals will be consumed, okay? So this is the most important chain breaking reaction in combustion. And again, because you see this always only depends on hydrogen and oxygen, this is the same for all hydrocarbons also. And then other important reactions here, of course, CO oxidation. CO is oxidized basically exclusively with this reaction 18 here, CO plus OH goes to CO2 plus H. That's the main reaction that consumes CO. And then you have a few others here, CH, other species, formaldehyde, methyl, radical, and then here's the fuel. And then here, of course, that's what I said earlier, the fuel is typically consumed here. Methane plus H goes to methyl plus H2. And that is neutral, radical neutral, right? And a few more here, but we don't need to discuss these. So now, if we look at the flame structure, this here comes from a simulation, and it shows here the temperature as function of, X in a 1D premixed flame, unstretched premixed flame, and it shows temperature. Here is the exponential increase. He wants to have a microphone. I'm loud enough. I don't need one. Yes, man, with batteries, I should have known this yesterday. No. Yeah, that's right.
I was looking for it.
Yeah, okay. So, and then also what you see in this figure is the hydrogen radical. And you see, I mean, we said earlier, there is a preheat region which is chemically inert. Chemically inert means there should not be any radicals because radicals would react. And you see indeed, when you hit about 1000 Kelvin, the radicals go to 0, okay? There's no radical here, on the in the preheat region, okay? So what we said earlier is correct. Here's another one that's interesting is that, while the temperature goes up, fuel here it goes away, but it first forms CO, and then downstream of this CO formation region, CO is converted to CO2, okay? And we'll see this also later on. So from what I just told you here, Peters and Williams have derived this 4-step, systematically reduced 4-step chemical mechanism, which is shown here on the next few slides. So the way this is derived is by making steady state assumptions. Usually in my combustion course, I would first tell you about reduced chemistry, but again, because chemistry here is a different lecture, I'm not, and you might not be familiar with this, but it's not so important maybe. But what we do is we assume that some species are in steady state. Steady state means they're consumed very fast compared to their production, and if that's the case, then, you know, a species that forms is always consumed very quickly, and the concentrations stay really, really small. And if I have a rate of change here, let's say dCA dt, and Ca is very, very small, then the rate of change also must be very, very small. And then we just say the rate of change must then be 0, and then here from the right-hand side, we get an analytic expression for, you know, for species concentrations. That's what we do. We assume that these are non-steady states, these are stable components, and then there's all the rest is steady state, except even though this is a radical and it is consumed very quickly, we want to assume H also to be not in steady state, so we see kind of, you know, how the radical, as a representative radical, so we can kind of see what's going on. Now, so H now represents the radical pool, and we said earlier the radical pool is changed by chain branching and chain terminating or chain breaking reactions. And we said the most important chain branching reaction is this, and the most important chain breaking reaction is this. And here's an interesting fact. If reaction number 1 here, chain branching, is faster than chain breaking, then radicals will increase exponentially, and you will get combustion, explosion, whatever, things happen. If reaction 5 is faster, then reaction 1 tries to make some radicals, but reaction 5 consumes them much more quickly, and then a flame goes out. You know, it will extinguish. Like you saw earlier, the regions where there are no radicals anymore. So the question is, which one is faster, reaction 1 or reaction 5? 5. Anyone else? 1. Anyone else? It depends. That's usually the right answer. A or B, it depends, okay? So, of course, it depends on the temperature. And it's very interesting now. I mean, in nature is so beautiful. I mean, here, I come back to Professor Law's beauty of science, you know, nature tells us now, this is the most important chain branching reaction, this is the most important chain breaking reaction for all fuels, basically. And both have the same reactants. What are the odds of that? You know, I mean, because this allows us now to compare these directly, okay? So I have this reaction, and I can just look at the ratio. What is the ratio of reaction rate number 1 and reaction rate number 5? And if the ratio is larger than 1, then chain branching is fast, explosion. If this ratio is smaller than 1, then chain termination is fast and flame extinction will happen, okay? Reaction rate number 1 is K1 times concentration of O2, concentration of H. Reaction number 5 is K5, concentration of O2, concentration of H, concentration of third body. And now, both depend on O2, both depend on H. H and O2 concentrations go away. Is that beautiful? Can anyone explain this to me? Think about it. This is your task for tonight. Yesterday, I gave you tasks that you should discuss during dinner. This is the task for tonight. I mean, how is it that these most important reactions in combustion both depend on the same reactants? And in the analysis, this goes away, and this just depends on K1 divided by K5, both just temperature dependent, and the concentration of, you know, third body. And the total concentration is just P divided by RT. That's the total concentration. So this is the ratio, and it only depends on temperature and pressure. Isn't that beautiful? And then I say, okay, if the temperature, so this is how this looks like. This reaction 1 in the Arrhenius plot, this is reaction 5 in the Arrhenius plot. And you see in this region here, this high temperature, this region reaction 1 is faster, in this region reaction 5 is faster. And so here, no radicals, all radicals are gone at low temperature. At high temperature, you know, I get you know, exponential growth and very quick conversion to products. And so the temperature where these two lines cross, which is where this ratio is equal to 1, we call this then the crossover temperature, or we call this the inner layer temperature. That's the temperature of the reaction zone. And that can just be determined here from this. And it's only a function, I mean, no, it's only a function of pressure, right? So for 1 bar, 1 atmosphere, you see this is roughly 1,000 Kelvin. This is exactly what we saw where the radicals go to 0, right? And for higher pressure, reaction 5 will be faster because it depends on the pressure, right? It depends on the third body. So this will be higher. And so at higher pressure, the crossover temperature is at higher values also. Okay? So, okay, that's, I find this very, very interesting. And again, this is what you should discuss at night. So now we can derive this, this reaction, the four-step mechanism. We identify the slow reactions and fast reactions. And, you know, the slow reactions are rate determining, and the assumption, you know, with the steady-state assumption, is that the slow reactions are rate determining, and then all these fast reactions, they happen infinitely fast, okay? So here we say O2 plus H goes to OH plus O, that's chain branching reaction. That is a rate determining reaction, it's slow, but then the conversion of OH, the conversion here of this O radical to OH and H, and then the conversion of these two OH radicals to H radical, this goes infinitely fast, okay? So I can cancel these out. This O immediately is consumed with this reaction, cancel this out. You know, now I have two OH, you know, this also cancels out. And if I add these three reactions up, this here twice because I have two OH here, then this is what I get. So what this means, reaction 1 is slow, but as soon as reaction 1 happens once, the other two, they go instantaneously fast. So this is what I see. If I would try to observe this, I don't see reaction 1 happening alone. Everything, the whole thing happens, this sequence happens at the same time. So this is what I see. So this is, again, is the reaction, you know, or the net effect of this reaction. O2 plus 3H2 gives 2H2O plus 2H. This is a chain branching reaction, and it forms two radicals. It's just like what we said earlier. Here's one radical, here's three radicals on the right-hand side. So if this happens once, you form two new radicals, okay? And then we do the same thing here with a chain breaking reaction. O2 plus H goes to HO2, and then HO2 very quickly goes to H2 plus O2. You add these up, you see here the HO2 goes away, and then this is what I get. Actually, also the M goes away. We just leave the M here to show that it depends on the third body efficiency. Okay, and then the fuel consumption, that's an important step. And so fuel, I said, is consumed with CH4 plus H goes to CH3 plus H2. And then we have the methyl radical. And the methyl radical is consumed with an O radical. Methyl radical is resonantly stable, is a very stable radical. And so it's consumed with the O radical. You need a very powerful radical to consume it. With the O radical, it forms formaldehyde plus H. And then that's an important step. And then the formaldehyde here is just, you know, by reacting with a radical to form this other radical. This here thermally decomposes into CO plus H. And then this is what happens. And then you have an O radical and so on. So I just add these fast shuffle reactions to convert all of these to hydrogen because my radical balance is in hydrogen. So you add all of these up, this is what you get. And this is now very interesting because if you want to consume 1 molecule of methane, you need to invest 2 radicals. The consumption of methane is a chain breaking step, okay? This is why methane is so slow, you know? Methane burning velocity is very slow. This is why, because you consume 2 radicals. Why do you consume 2 radicals? Which reaction here consumed the 2 radicals from the elementary reactions? Where did the reactions disappear? I told you in the beginning, rule number 2, when you see a reaction, first count the radicals. You shouldn't even have listened to me. You should have just counted the radicals. And then you should have seen there's one reaction that consumes 2 radicals. And then, you know, red light and so on. Which one is an easy, that's an easy question. That shouldn't, yeah. Exactly, the consumption of the methyl radical. Here you have 1 radical, 2 more radicals. So 3 radicals on the left-hand side, 1 radical on the right-hand side. That's because methyl is such a stable component. So anytime you have a methyl radical, remember this, it makes a combustion slow because it's usually consumed here with the O radical. Okay, so and then a CO oxidation. So here we form CO, and so we need to oxidize the CO also. I said this is always oxidized here with this. I add this fast shuffle reaction just to replace the OH with an H, and then I add these up and I get this so-called water gas shift reaction, right? So these are the 4 steps here. These are the 4 reactions. This is the fuel consumption. This is which converts fuel into stable intermediates, CO and H2. Then I have the oxidation of CO to CO2. I have the oxidation of H2 to H2O, which is at the same time also a chain a branching reaction, and then I have a chain breaking reaction also. Okay, so these are the dynamics of a flame, and this really includes most of what's of interest. Now these global reactions, they're always, because we said they are initiated with a slow reaction. So the reaction rate of these is always the reaction rate of the initiating reaction here, 11, 9, 5, 1, whatever these were. Okay. Oh no, here they are, right? Okay, and then this is how this is complemented. If you want to use this in a numerical simulation, but we don't need to discuss this. How long are we going to go today? 6:30 or? Now 5:30 is now. Okay, good points to break. Okay, enjoy the evening. See you tomorrow.